So let's continue on and let's start talking about our multi-layer protocols. We're going to talk about SCADA, Modbus, and DMP3. Now SCADA is supervisory control and data acquisition systems. Sounds like a mouthful. They are the type of systems that actually monitor and control, say, our industrial processes using computers. These are the systems that control the robots that move, say, in your car manufacturing plants. These systems can also be in control of, say, our water systems, our power plants, nuclear power plants, coal power plants, the water treatment systems, like I said, because it's easier for us to have a centralized system that can manage the switches, our natural gas, if it needs more or less pressure, the water systems, if they need to open a valve or close a valve, instead of sending somebody out in the field or having somebody there in that part of the warehouse. They can use these SCADA systems to take care of this. Thinking about building cars and car manufacturers. I mean, those robots are going a mile a minute. It would take manual labor, human labor to hit those welding spots. It would take us longer. We couldn't, produce as many vehicles as fast as, say, this automation does. So these SCADA systems, like another example, they use for monitoring, controlling the processes for power plants, like I said, oil and gas transmission lines. So you got oil and gas transmission lines that go for miles and miles and miles. Well, you might not want to send somebody out there for that. Those are large-scale systems. Food and auto manufacturing are considered smaller scale systems, as a matter of fact. Now, these also be known as industrial control systems, ICS, or distributed control systems, a DCS. But these SCADA systems, they're big systems in themselves, not physically, but the way they're implemented. Because we have a management station, you take this management station, and this is part of the SCADA system that talks to controllers in the various locations of whatever it is you want to do. Like the oil and gas transmission lines we were talking about. If they need to monitor those lines, or if they need to open a valve or close off a valve, the management station talks to a controller, a PLC controller, a programmable logical controller that does whatever it is we tell it to do, or whatever it's programmed to do. If we hit a certain button on our SCADA system, on our management system. They used to use this in a job I used to have to control the air around all the buildings. We had like 8 different buildings, and they had a management station up in maintenance, and they could control the dampers inside of the ceilings, right, to allow more or less air. They could control the temperature all from a centralized location. Controlled the HVAC systems throughout all the buildings and all the rooms. They had a little map. It was really nice. They just actually click on it. They could turn it up, turn it down, open it and close it. That way they don't have to manually go to that building, go to that room, get up in the ceiling and manually change it, or have people changing the temperature all the time in the rooms, right? It's centrally managed now. And that's a cost savings because you don't have people turning it down and everything kicking on and turning it up and everything, the heat kicking on. It's centrally managed, and it's designed to save money, to save that bottom dollar. Now, you might have something called Modbus with our SCADA systems. This is simple communications protocol, kind of like Telnet and FTP, which should tell you what? Because we've already talked about Telnet and FTP, and we said they're what type of protocols. If you said unsecured, that's right. Because remember, we were using Telnet or FTP, and we had Wireshark or something like that, a protocol analyzer, wire sniffer, network sniffer hooked up there. We'd see those credentials going across in plain text, the username and password, not secure. So Modbus is considered a client-server type of architecture where the client sends a request to the server and the server is going to respond. So the server could be like those PLC controllers, where the client is us. We send that information off. Now, the client is considered the master, which would be you or me as the controller sitting at the management station, and the server is the slave. Now, this protocol was also designed to constantly poll the servers for information, right? So I'm always asking, is everything okay? Is everything okay? Is everything good? We got a green, thumbs up, whatever you want to call it. Is everything fine? Do we have flow through the gas line? Do we have good flow through our oil line? Is there something wrong, right? We're always asking for this information so we can have a good report on our management station. Now, security in Modbus, like confidentiality, authentication, authorization, and integrity or access controls, not really designed for this protocol. All right, this is more of a quick, simple, lightweight protocol. However, it's not very secure. Again, think about what we said. It acts and is similar to Telnet and FTP. And we know Telnet and FTP gives us no security. There's no confidentiality. There's no encryption there when it comes to our data or our username and password going across in plain text. Then we have DNP3. Now, this is a more recent communication protocol than Modbus was, or is, I should say. Now, this was originally designed for electrical systems. Still, we're still talking about the SCADA architecture here, but this was designed for our electrical systems. Has some improvements over Modbus. So rather than polling, right, it's always asking that server, right, so just everything okay, everything okay, everything okay. The DNP3 servers, the controllers can initiate responses when any change is detected. So now we can do something about that. Now a controller can send multiple responses in a single response to multiple requests from a client. So instead of asking one question at a time like Modbus does, DNP3 can send multiple responses. Now, about multi-layer protocols. Still issues with security when it comes to our multi-layer protocols. Now, some of these systems, these SCADA systems still that we're talking about, have been ported to more traditional operating systems like Windows or Linux. So we could have a Linux-based management system, and it could be controlling the SCADA system. Now, SCADA systems in their own right have some security flaws, right? There's no antivirus protection, for example, no malware protection when it comes to that. Now, when we port these over to a traditional operating system that people may be more familiar with, now we're adding on another layer of complexity, and we're also adding on another layer of vulnerabilities. Because now we not only have to think about the SCADA system and physically protecting that, physically securing that system so people can't get to the PLC controllers, they can't get to the management station in the control room. Now we also have to patch our operating system, make sure it's updated. Are there the applications that are on there? Make sure they're updated. What type of authentication do we have to get into the management system? Because most of the time with these SCADA systems, you have a big control room, right? The only authentication or access control I need to say that you can have is to lock the room. Don't let them in the room, because there'll be a panel, right, of buttons and switches and dials and monitors and things of what's going on. And if you can get physical access, now you can control what's going on, right? It's not like a computer where you sit down and you have to log in and authenticate yourself. So this gives us, I guess, a layer of security if you want to look at it that way, but we also have to keep up with that now. So are the engineers that are responsible for this system, are they going to follow policy? We're going to have to come up with a security policy, password complexity. You know, some of these systems may be remote. If they're remote, what does that mean? Well, they're going to require remote access. Now they may be able to touch the internet. So if you have a remote system and you have to get to it as an administrator of that organization, If you remote into it, you're going across the internet. Unless you have a dedicated link, you're going to go across the public internet. That may be a vulnerability for you. That may be against company policy. We're going to talk about tunnels later. Maybe you need to create a tunnel between you and that remote system. So that traffic is tunneled now, and it's somewhat private as it goes through. That gives us that layer of confidentiality. A couple things you just have to think about there when it comes to these multi-layer protocols. Now we also have converged protocols, and we've been doing this for a long time now. A converged IP network is a single platform on which we have these interoperable devices, and they can be run in different ways, in innovative ways. Think about how we used to do networks, or if you don't know, this is how we used to do networks. At first we had telephone lines, right? Analog lines coming into your house. Everybody had the telephone. And then the internet started to take off a little bit. People started to get online. Well, to get online, you had a modem in your home. And that modem would call out through the phone lines. So we had existing infrastructure, all these telephone lines everywhere, and we would use those lines for data transmission now. We would call out with our modem. Well, it's kind of come full circle now. And now we have data lines running everywhere because they're faster and better than the old telephone lines. So we started running data across these broadband lines. But now we're sticking everything else on these data links as well. We're sticking video on there. We're sticking VoIP on there. Audio, streaming stuff, right? If you think about your cable into your home, right? If you have cable or satellite, because you can get it through satellite too. You may have one cable running to your house, right? And it's screwed in there. But in that one cable, you're getting your video for your TV, and you may also be getting your internet, depending on if that's how you do it with your internet service provider. So they're converging protocols there as well, right? The video from your cable television or for your cable television, and the data for all your internet connectivity. We can do this as an enterprise. We can take our data connections, right? Our Cat5, Cat6 cables that we have, all of our switches and routers and everything like that. And what we can do is take the data that we have and put voice on it, let's say. So now we can run voice over IP inside of our network. And when we do that, we're converging those protocols. It also allows us to have fewer network components. Instead of having a switch and a router for the voice, and a switch and a router for the data, and a switch and a router for the streaming media that we're going to have. We converge all this, and we use one switch. And yeah, it may be a little bit more powerful switch than what we needed at first, but it's still cost savings. It's very scalable when we do this. We can grow as needed. All right, so converged protocols are outstanding. It is a better utilization of resources because we can use solutions like QoS, quality of service. So like in VoIP, let's go back to VoIP, the voice over IP. We have data connectivity inside of our office, inside of our organization, but we're also sticking VoIP traffic on the same line. Well, now we can use quality of service because that voice traffic has to get there, right? There can't be jitter or latency on that line. So we'll set up quality of service, and that gets priority on that medium. Our data is still going to get there, but the voice needs to get there first, right? It always has to be in front of the line to make sure those data packets are flowing back and forth for that voice communication. Because it's not like if you miss a word or 2 or 3 words, that it's going to resend it later. You're going to have to ask, and I'm sorry, I didn't get that. And then the other end's going to have to repeat themselves. It's not like that with data, right? TCP, if it doesn't get there, it'll ask for it again. And it'll send it again, and everything will be fine. We also have fiber channel over Ethernet. All right? So we can take our Ethernet, our existing Ethernet, and run fiber channel over it. Again, very scalable. We can run different things on this. This is a lightweight encapsulation protocol, but it lacks the reliable data transport of the TCP layer. So this is a layer 2 non-routable protocol because it's on our Ethernet, right down there in the data link layer. So it doesn't incorporate TCP or even IP protocols. So key things we need to think about: fiber channel over Ethernet. It is fiber channel over Ethernet, so we're taking advantage of existing infrastructure. We don't have to run more, but this protocol is not routable. It's usually for this short haul communications within the data center. We're not going to run this down the street or run this down to the next room or anything necessarily. We're going to leave this in the data center itself because it's very fast, but it has to be somewhat short runs. Ethernet, you can only go up to 300 feet anyway. Multi-protocol label switching, MPLS. This is a newer technology. It's been around for a while, but this is a newer technology, usually out on the WAN. All right, you don't run this on your LAN, your local area network. You probably don't run this at home unless you've got a couple routers that you're practicing with. But this is a WAN technology. And it's best described, best summarized as like a 2.5 layer. It's in between 2 and 3 when it comes to the network protocol. So in the traditional OSI model, layer 2 covers protocols like our Ethernet, like we talked about, and the SONET, all right, which can carry IP packets, but over simple LANs or point-to-point WANs. Now, layer 3 covers internet-wide addressing and routing using IP protocols, and we saw that. We know layer 3 is responsible for our routing. So MPLS, what that does is sits between those 2 layers. So we got 3 and 2, and we got MPLS right in here, about 2.5. This provides additional features for the transport of data across the network. So MPLS can actually allow fewer route lookups for routers along the path because it has labels on it. And switching is faster than routing. So having MPLS on the back end means when it hits that first router, it does a route lookup and it assigns a label. So when it gets to the next router, that router doesn't have to look up anything. It doesn't have to do a route lookup through its table. It goes by the label and knows exactly where it needs to go. So it moves that direction and goes that way every time. So it's a little faster than traditional routing, and that's the way they're moving towards that MPLS. We also have iSCSI, Internet Small Computer System Interface. Now this is IP-based, which means it's routable. Now this is often seen as a low-cost alternative to that fiber channel that we talked about earlier. This is very popular in data centers like your storage area networks, because you may have a storage area network on this network over here, your production network over here, development network over here. We can all reach that data network still, that storage area network, because of it being routable. And then VoIP, I've talked about that a couple times already. Voice over IP, or VoIP. Now this is making calls using broadband internet connections instead of those old analog, I guess I could say old, the older, let me say that, analog telephone lines. You know, we had those growing up, right? You had to be so close to the wall until we got the cordless phones, right? And then that was the greatest thing ever. But you had to plug in RJ11 connection into the wall, right? And you get an analog signal. You pick it up, you hear a dial tone. We still have dial tones with voice over IP, but now we're using digital signals. And we're using the existing data connections that we talked about to run our VoIP over. And we're going to talk about that a little bit more. So let's switch gears a little bit and talk about wireless and understanding wireless networking. Now there's a couple modes that we can work in when it comes to wireless networking. We can work in infrastructure mode, and we can have an ad hoc mode. Let's talk about ad hoc mode first, since it's the shorter of the two topics. In ad hoc mode, I could set up a laptop here and a laptop here, for example. and I could set up my wireless, turn on my wireless card, and turn on my wireless here and put it in what's known as ad hoc mode. Ad hoc mode allows me to talk from laptop to laptop or device to device. It's not like I'm going to talk to hundreds of devices. I'm not supporting hundreds of devices or dozens of devices for internet connectivity. I just want to talk to that one device. It's kind of like if we took a crossover cable and I plugged it into this laptop's network port and I plugged it into this other laptop's network port, and we could pass data back and forth. That's what an ad hoc network is when it comes to wireless. I used to use these in presenting, right? I would have my laptop set up and have it hooked up to the projector, and I would walk around with my tablet. But my tablet and the laptop were on an ad hoc network. Only those two were communicating, so I could control the presentation software with my tablet. So when I moved my finger, the students would see it on the board. I could highlight and underline because of that ad hoc wireless connection that I had. Now we also have infrastructure mode, and this is the one probably everybody's more familiar with. They probably maybe just didn't know that it was called infrastructure mode. Infrastructure mode means you are connecting to the existing infrastructure inside of a building, or you're using a wireless access point for connectivity. Now in your home, and I'm just guessing here, you probably have some type of connection coming in from your internet service provider, and you're hitting some type of router. Now that router, which is also acting as your modem more than likely, can have built-in wireless nowadays, or you can go out to the department store, your favorite one, wherever you do your shopping, and buy a dedicated wireless router. You'll plug that into your modem or your router that you got from your ISP, and you can broadcast out those signals to wireless devices like your tablets, your cell phones, your laptops, your gaming systems, your TVs, all those that we talked about a little bit earlier. That's now part of your infrastructure, because that original modem and router is your infrastructure. Every connection to it is part of the infrastructure. Now we put this wireless router out there, and all our wireless devices are in infrastructure mode. They're part of your network. Now there are a couple different standards that we need to be aware of. 802.11, anytime you see that, you need to immediately think wireless. But we need to be familiar with the A, B, G, and N standards. Now the little chart here that I got, you can see 802.11 A, B, G, and N as we go across, and the different frequencies, the transfer rates, the range that you may get with those wireless access points, and the compatibility, which the compatibility is important because it's backwards compatibility. So the frequency, we have 5 gigahertz and 2.4 gigahertz. Now 2.4 gigahertz is a pretty popular band nowadays, and it's actually pretty congested. The 5 gigahertz is a little bit better if you want to look at it as far as not as congested. There's not as much things inside of that band. So the 5 gigahertz, like the 802.11n, runs in the 5 gigahertz or 2.4. So it will try 2.4, and if it's too congested, you can have it run in 5. Or you can tell it just 2.4 or just 5. That frequency line, though, is what we need to focus on when we're thinking about backwards compatibility. Because if we have our 802.11n, let's say in 5 gigahertz frequency, it cannot talk to an 802.11b or G wireless access point. They won't communicate because one's talking at a 5 gigahertz, the other one's talking at 2.4. They're never going to see each other. It can, however, talk to the 802.11a because they're on the same frequency. So you have to be mindful of that. If you have a G router in your house and you go buy an N router, you're going to have to put that on the 2.4 gigahertz frequency so they can communicate, unless you want them on separate frequencies. And that's not channels, okay? Or you might be thinking, well, I've always been told to put on different channels. It's not what that means. These are frequency ranges, and you're going to have to put it on 2.4 so they can communicate. Now the transfer rate, those vary. You know, These we have here on this chart are actually pretty close. 802.11G, 54 meg, you can get that. 11 meg with B and 54 with A, you can get those too. Now the only thing about A and B is the distance. You can see A doesn't go as far. It's faster than B, but it doesn't have the range that 802.11B has. Now N and G, they both have 300 feet. But G, again, is 54 megabits, where N jumps up to 600 megabits. And that's internal traffic. So don't look at this and don't look at the back of a box and think, well, I'm going to buy this. It says I can get 600 megabits. Because if you only pay for a 15 megabit connection into your house, you're not getting 600 megabits. It's not going to happen because you don't have that coming into the house. I hope that makes sense. Now this means it is able to transfer that fast, and you might get that, say, from a laptop to a laptop, working in infrastructure mode using the wireless access point as the switch. It's possible. Again, though, you're only as strong as your weakest link. So if your wireless router is running 802.11G, but your two devices have 802.11N, what's the fastest we're going to go? 54 megabits, that's right. That's going to top out. Even though these guys can scream out 200, 300, 400 megabits a second, the weakest link is going to be our access point. So it's going to throttle us back just by default of how it's engineered.